acknowledge this land on which the Fields Institute operates. For thousands of years, it's been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. Now I'll turn things over to Zhenhong Wu, who will introduce our speaker today.
Thank you. Good day for everybody, and I'm very happy to have Bouchra, Professor Nasri, very own members of the network to speak today. And Bouchra is a professor of in biostatistics from the Department of Social and Preventive Medicine, University of Montreal. She is a junior scholar funded by Focus in artificial intelligence, health, digital health, and among many other things. Bouchra is a member of the NSEC PHAC funded initiatives, is a member of multiple networks, including our own, M4PH. I'm very glad that she's talking today in subject that very much of my favor. It's like dengue and spatial-temporal Markov chain, Markov region switching models. So here it is, Bouchra. Thank you.
Thank you so much, Zhenhong. Thank you to the MFPH for inviting me to give this talk today. Today, I will be talking about the Markov regime switching models with an application to dengue data in Colombia. This is mainly work of my MSc student, Rauda Berkat, who she is now at PHAC. She completed her MSc recently and joined PHAC. And my PhD student at HEC Montreal, who already found a job without finishing his PhD. And my colleague, Kate Zinzer, she is expert on epidemiology for infectious disease. And this work is mainly funded partially by CIHR and INSERC. So the methodological part is funded by INSERC and the application is funded by CIHR. So I will start by maybe defining what we want, what is the methodological or the theoretical model, and then I will give an overview on the application that was mainly part of the MSc thesis of my student. So most of this work is mainly based on the effort of my HQP, so I don't take any credit of most of the work here. Basically, when we are dealing with infectious disease, we are mainly dealing with time series that often comes from multiple locations. So one, we have the serial dependence, so the observation of today depends on the observation of the past. And we have multiple locations, so we can catch the spatial dependence between all these time series. So if we can have, for example, the case of COVID, we have COVID in multiple sites in Quebec, and we have data daily that depends on what we observe in the past. For example, if we have an outbreak in last week, this will impact how the trajectory of our cases will behave in the future. So in this talk, I will mainly focus on regime switching models for a simple reason. Why is the fact that when we are dealing with time series generated from observation that are dealing with cases of infectious disease, we can mostly observe the fact that at some point we can have like a hotspot or a highest number of cases, and then at some point we have lowest number of cases. So our distribution behave depending on if we are in this distribution or in lowest distribution like here. So basically we can find that our distribution depends on what we call regimes. So what does mean? It's that our distribution can behave differently if we are in the case that we have a high number of cases or low number of cases, which is not the case if we are taking a regular time series and we are just modeling regarding the past, for example, in the autoregressive way to model time series. So here we have like kind of regime and fluctuation between regime that I will describe later. So what is a hidden Markov model? Basically depends on two different sources of randomness, a finite number of state or regimes. So in our case, we can have a state that have a highest number of cases and a state that have a lowest number of cases, for example, and the dynamic is modeled between switching from a highest to lowest number of cases. This dynamic can be modeled by a stationary or non-stationary Markov chain, and the observation, the distribution of the observation depend on the regimes and possibly observation from the past and covariate. So often in the literature, the probability distribution belong to the same parametric family, and the parameters depends on a regime. For example, we can take the Gaussian HMM, and each regime will be modeled using a Gaussian distribution. So in this model, we can have like the regimes denoted by tau1, tau n, and distributed as a finite Markov chain with values in the set 1 to L, with a certain transition matrix that catch the transition between one regime to another. So here is a very simple figure that describes the dynamic of hidden Markov model with two regimes. So basically, if I am taking like a sample example or a very basic example, like the first regime describe the regime where the cases are very high, and the second one where the cases are very low. And here we have the probability to stay in regime 1 and the probability to stay in regime 2. And the dynamic between this, the probability to goes from 1 to 2 and to goes from 2 to 1. Basically, very intuitive example to explain the regime switching model is the fact that we have like it's the weather. So we have a sunny day and a rainy day. So what is the probability to stay in sunny day? What is the probability to stay in a rainy day? And what is the probability to switch from a sunny day to a rainy day, and vice versa? So here, and those probabilities can be also, can have other interpretations. So those interpretations are linked with the persistence of staying in one regime. So we can also calculate the number of runs or how many days we can stay in one one regime or another regime, for example, how many days we will have all those highest cases and how many days we will have all those lowest cases, and we can take the mean and say that we can persist more in regime 1 or regime 2, and we can have more regime. We aren't like we can have like 3 or 4. It depends on how complex our data they are. So if we take some notation here, so as I defined before, we have the hidden state or the regime as tau t, and we have our variable of interest yt, and zt denote the vector of covariate. So if we denote it by f t minus 1, the sigma algebra that generate the past, the information from the past and covariate, and jt minus 1, the sigma algebra generated by the past information of regime, and f minus t. So if we state that xt, it's all the information that give us that include all covariates for us, such as the past information as well as other covariates. It can be temperature, precipitation, or other kind of covariate. And we can define what we call the autoregressive HMM model with covariate, which is defined here by ARX HMM, which basically it's the HMM model, but we include the information from the past and the covariates. For example, if we are modeling the dengue data and we understand that the dengue data depends on temperature and precipitation, so and it depends also on how the cases behave in the past. So basically, we can model this using HMM with the information from the past, so which include the cases in maybe the past weeks and other covariates, for example, the temperature, precipitation, and so we can define also the transition matrix like this. And as I said, each regime has their own distribution, and it can be a continuous distribution or semi-continuous distribution depending on the data. So, for example, in the case of infectious disease, we can have a lot of data that have a lot of zeros, because at some point we don't have any cases, and then we have some cases, and then we have like a highest number of cases. So it can also be a zero inflated distribution, which take into account the fact that we are at some point we don't have any cases. Or it can be other type of distribution, like if we are in other area of research, it can be other type of distribution, such as the Gaussian distribution or other kind of distribution. So basically, the joint conditional density of tau and y, which is our variable of interest given our covariates, including the past, can be given like this, with respect to some reference measure, which can be a combination of counting and continuous measures, or a continuous measure depending on the kind of data that we have. So we can estimate this kind of density using the expectation, the EM algorithm. And it's well known in this kind of model to use this algorithm to estimate the parameters. We can also use other kind of estimations, and I saw in some people in the audience use also a Bayesian algorithm, and so to estimate the parameter of the model. Some estimation methods are better than others. The EM algorithm have some issues regarding the estimation. We noticed that a couple of times when we were doing some goodness of fit test to select the models, that at some point it wasn't that efficient to use this kind of model, this kind of algorithm, but we didn't try to understand how efficient the other algorithms are to estimate the parameter. I know that there are a lot of new articles about the estimation, especially when we have spatial data, that it's worth investigating to improve the estimation of the parameters. So, as I said, and we can combine this information, this kind of model, which is used for to describe the temporal behavior of our time series, to a spatial dependence, and basically we can include the information, the spatial dependence, using several ways. And one of the basic way to do that is to include the information from the neighbors as a covariate. So, for example, we can include all what we have, like this specific site, and all the neighbors have some specific information. So we can know that in the very close city, we have maybe a time series for the cases, and we have a highest number of cases. So we can believe that because of the distance, we can get also we can get also we can have highest number of cases very soon. So we can include those information as a covariate, and then model build our model and get some result. We can also consider some more complex dependence approaches, such as Copular function. So what is a Copular function? So if we consider every site here, so here we have information in every site that we have. So we have our time series for every site, and then we are trying to catch the dependence between all of this information. So we can use what we call a Copular function. And what is the Copular function? It's basically, we will find the joint distribution between all the information in all those sites by using a Copular function here and taking into account the marginal information that we have. So in every site, we have a specific model. We have specific HMM model that that we build for every site. And then those models can be all combined in a copula function that gives us the big picture about the dependence between all those sites. So it is not very straightforward to do it like this. We need some transformation and everything to be able to build the model. But we, in one of our papers, we saw that using copula may improve the prediction for, in this case, in this spatial dependence, in comparison with taking only the information from the neighbors. So it's also a little bit tricky to use copulas. One, because we are dealing also with semi-continuous distribution. So copula here is only unique when all the margins are continuous. So when we have discontinuous margins, the copula are not unique. So it can also have a lot of problems with identifiability of the copula and identifiability of the parameters. So under some specific conditions, we can use the copula, and those conditions we can verify them in our setting of the data. There are other ways to use the copula for dependence when the margins are semi-continuous, but the estimation of the parameter are not very precise. We can use what we call the jittering method. It's like using some noise that makes our margins continuous, and then use the copula. So we will not have some issues of identifiabilities, but we will have less precise parameters. So it's good to use the copula for the spatial dependence, but make sure that it's good in your case with your data, especially if you have like zero inflated data or other kind of data that are semi-continuous. So here I will not go more deeply in how we define all this, but I just give you an overview that it can be used in our case by taking all the information in every site. And what is good to use the copula in the spatial dependence for infectious disease is the fact that in every site, sometimes we have a very specific distribution of the data. So we can see for example, in one site, we can have data that behave using only 2 regimes, another site it behaves using 3 regimes, and so. And we can also have a different distribution for the data. We can see that sometimes we are in one site that we have always all-time cases. So maybe the distribution is different from one site that we have cases only in the summer, but not cases in the winter, and so. So assuming that all the sites have the same distribution, it's very strong hypothesis. So the way here to construct the dependence using the copula is the fact that we can also have specific information for every site, and we can combine all this information in the model using the copula. So here we can also derive like the conditional CDF and so I will not go deeply in details here because I only have 15 minutes, but you can see our two recent papers on the estimation of the copula when the margins are semi-continuous. So it gives you an overview about the estimation and also the condition that verify that you don't have any problem of identity variabilities and so. So here is the paper that are now submitted, and as I said, it gives you an overview how to estimate the parameter correctly, taking into account the good conditions for your setting. So then I will talk about the second part of the presentation is the dengue data that we used in my MSc student, my former MSc students. And what was the interest of her work is to identify if there are any environmental predictors and that influence the dengue incidence in the META department in Colombia between in the last almost last years. So I guess you are all you all know very well the dengue fever, and it's transmitted by infected female mosquitoes, the Aedes, mostly in tropical and subtropical regions. So a study that was acknowledged in WHO estimated that the burden has increased significantly in the recent year, reaching 319 million cases yearly of dengue. And why Colombia is it's of our interest in for the modeling part is because the average case fatality rate of dengue fever in Colombia it's higher than the other countries in America. So we are interested on the META department, which is here, which is one of the department that have the highest number of cases in Colombia. So the META department is composed of 29 sites, 29 municipalities. And here is the biggest municipality of this department. So as I said, the META department is among the most affected departments in Colombia. And here we can see the incidence rate of dengue over years. It's basically aggregated data, the aggregated cumulative incidence of dengue for each year. Here we have 2011 and 2019, and we can see in 2019 and 2015 we have basically the highest number of cases. Some of the municipalities here show also highest number of cases in 2016. But as I said, I'm just aggregating the data, so we cannot see it in this figure. But if we look at the data for each municipality, we can notice that some municipalities have their peaks on 2016 and not 2015. So here we can see the dengue changes over the years in the meta department, and I'm showing you only 2015 and 2019, which are the most the years where the dengue was mostly affected the population. So we can see that mainly the dengue data, we have highest number of the dengue data in this area, and it was not the same clearly in 2015, but we can also see in the similar area we can acknowledge that we also have highest number of cases. So except in those 2 years, the distribution of cases are basically similar in all the municipalities, with some exception that are mainly in this specific area. So why we are interested in environmental factors for the dengue? As you know already, that the spread of the disease basically depends on the vector lifestyle and their reproduction. Many environmental data and also socioeconomic and sociodemographic factors. So in this work, we are mainly focused on the environmental data. We don't take into account other factors. The fact that we are not taking into account other factors may lead on very biased estimation, and we will talk about all the bias at the end of this talk. So we focus mainly on 4 covariates, which are the temperature, precipitation, humidity, and the pressure. We use remote sensing data to have all those variables. So here we can see the distribution of temperature and precipitation in the meta department. We can see that the highest, here I am just plotting the temperature and the precipitation, the aggregate values from May to July for both variables. And we can see that the precipitation is mainly around 4 to 12, and temperature can go up to 30. And it's mainly, the distribution is not clear for both variables. We can see that at some municipalities we have temperature that can go very high, and other municipalities we can have very different type of observation. It's basically very low temperature in some municipalities here, comparing to others that are located mainly here and here. And it's the same for the precipitation. It's not clear the trend depending on the municipalities. So we can also acknowledge that the distribution of every site, it's basically different from the other site. So I didn't put any figure for the other covariate, just to not overwhelm you by figures, but you can also go and see the MEC thesis of my students to have a complete information about the distribution of other variables. So here I'm just plotting some result that we have regarding the precipitation and other covariates. So in this figure, we have the relative risk according to the lag of precipitation and some values of precipitation for 5 municipalities. Those 5 municipalities are all located here in this part of the Meta department, and basically it catch a little bit what is happening in the other municipalities, what are the trends in other municipalities. So basically we can see that highest amount of precipitation with some lags can give us a highest risk, relative risk. We can see this basically for a couple of no, I'm misreading this. Okay, here we have the lags, and here we have the values of precipitation, and you have the relative risk. So we can see that we are talking here about lag 5 approximately, and the highest amount of precipitation. We can have the highest risk of having dengue. It's the same here. We have a little bit different different behavior here. So with the lag 20 impact more the relative risk than the lag 5, but overall we saw that lag 5 and lag 20 are the most have the most impact on our risk, relative risk for the precipitation, and we will see this after in the next. So we can also observe some similar trends for the temperature, and basically the temperature don't impact that much our relative risk, and not as much as the precipitation. The precipitation was the first predictor that have impact on our relative risk, and then we can have the temperature. So we can see that at some point the temperature with some specific lags that impact give us a highest relative risk. And most temperature don't have any impact on our results, which is not the case here. We have a couple of lags that impact our result, so it's not that clear for temperature. It's even worse for the other two predictors. So we can see that for us, the humidity don't have mainly any impact on our data, and we notice the same thing. So we can see that the risk ratio is flat in some municipalities, and it's almost below 1 everywhere. And we can see the same thing for the pressure. So here I give you overview on the spatial distribution of our relative risk with the associated lag and the quantile of precipitation. We can see that with the lowest amount of precipitation, if we are taking the quantile 75, the risk is almost below 1 or between 1 and 1.2, 1.3, which is not the case if we have a lot of precipitation, that the risk can go up to 2. So it's the same thing for temperature. It sounds like highest temperature also impact our risk, which is not clearly the case here. So our risk, it's almost between 1 and 1.05, which is not the case here, that the risk goes to 1.1 or 1.2, depends on the municipalities. So I am on time. So as conclusion, if we saw the maximum values of the risk ratios, the temperature variable reach their peaks mostly at 20-week lag. So the data from 20-week lag influence the dengue incidence, which is not the case for the precipitation. It seems like the highest risk ratio are mainly in week 5 and week 20. We don't see any impact of the sea level pressure and humidity on the evolution of dengue for this department. And we saw also in some other results than Northwest region have some similar tendencies in some cases, which indicate that there are partially geographical dependence in our data. So unlike other studies in literature that found that the sea level pressure and humidity demonstrate some impact on dengue incidence, we did not find this in our study. We also acknowledge that there are a lot of bias that will impact our estimation, which mainly include the ecological bias, which means that the distribution of all our information regarding, for example, the temperature and the precipitation in one municipality is not the same, which impact that the fact that our estimated relative risk are not the same in maybe one part of a municipality and another part of a municipality. We also have information bias, so our data are only collected from a surveillance database, which include only cases that have been reported and not the real cases of dengue in Colombia. And it's real cases are very high than those reported in this database. So we acknowledge that we don't have the exact information about the cases in Colombia. We also have confusion bias, so we did not include any socioeconomic or sociodemographic factor which can really impact our results. The dengue did not behave the same in every like in if we take into account the socioeconomic and sociodemographic factors, so we can see that the dengue incidence will not behave the same. So we acknowledge that we did not take into account any confounder in this study, so that also will impact our results. So inclusion of this factor will also help. And at the same time, we also did not include in our study any intervention that have been done in Colombia regarding the prevention of the dengue mosquitoes. So that's also can impact our results. So here are results that did not take into account any of those information. So if you are using those results, be careful to report all those biases that we acknowledge in our study. So thank you for listening to me today.
Yes, thank you very much, Bouchra. All right, so if anybody has any questions, feel free to raise your hand or put them in the box below. Oh, we have Shock. You're still muted.
Yes, thank you. How do you interpret the relative risk, which is different in different subregions as a function of precipitation? So you mention it as maybe it's at sea level, or so it's the local topography that will make a difference? Because in terms of public health recommendations, I mean, you cannot say region A, don't worry about the rain, and region B, pay attention to the rain, right?
Oh, you are right. I think it might depend on you are saying that the fact that there are different between that other factors can also influence the estimation. So it's difficult to have a unique conclusion for every municipality, which is right. I guess that if we want to make it like if we want to make a conclusion from this, we need to take into account other confounder that give us the almost real risk, relative risk, because here it's just preliminary. We don't know what other factors that can really impact our estimation. So I guess the answer is yes. We need really to understand a specific characteristic of each municipality to understand how to interpret all those results, which we did not do yet.
So it would be like a weighted sum of different factors, and in some subregions precipitation is more important than in others.
Exactly, because it cannot behave at the same. If it's raining in one city, we can have like one amount of rain that can, for example, flood one city but not flood another city, depending on. It's the same here. So it's need more digging into the understanding of the geographical characteristic of each region to understand if this amount have any impact or not, to have a specific recommendation to the public health agencies.
Okay, thank you.
So my question to Jack is, are you asking because it's not actionable because you cannot really prevent precipitation, or?
No. It's just in terms of well, actionable information. If you try to pick up the most important variables or the factors influencing incidents, if precipitation is important in one region, you have to be able to argue why it's less important in another region. So it may have to do, as you mentioned, Bouchra, some regions are more prone to flooding, or it's the topography and the rain falls but then drains, and so in terms of mosquito population, so That's why I'm trying to figure out if precipitation is important, it is important. So it's important everywhere, but there's a question of weighting and how important it is and what are the confounding factors.
Yeah, exactly. I do agree. Because I think, yeah, I think also the confounders are important.
Yeah,
because in digging on all those historical data, we don't really take even into account all the interventions. So maybe like there are no impact of precipitation, you know, but there are just more intervention in some municipalities rather than others. So it's difficult to really have an association. And it's more descriptive way to do things. So, hi Alex, how are you?
Oh, Bouchra, I'm fine. And you?
Good.
Thank you for the interesting talk. I know that this topic is of high interest to me. I think one of the issues, I'm sorry, I was disrupted here and I missed some slides, so I have two questions. One point that I don't understand, how many states do you have in our Markov switching model and what do they represent?
Oh, we had 4 states in almost all the municipalities, except some of them that we had less or more than that. We don't clearly understand what they represent. We just like we guess what they represent. We can say that one state, it's we have a highest number of cases. Then we have like cases that are more in the median, and then very low cases. And one of the states are maybe zero inflated, like it's more 4 zeros. So it's basically 4 states that we have for almost all the cities.
And the probability to, let's say, navigate among the states is a function of the covariates that you are describing.
Yes, it is. Yes, it's in this case, yes, it was because if it is not a function of covariate, it will be tricky to justify that like a variation of precipitation in this case.
I'm just trying to understand where the covariates entered in the model. So going back to Jacques' discussion, how did precipitation and temperature enter in the model? They entered contemporaneous at time t or lagged?
They were lagged. It's that the precipitation were lagged.
How did you decide about the lagged? Because I think this goes back to Jacques' discussion, because Lais, who is also attending the talk, has a paper. One of her PhD thesis paper is on chikungunya, modeling cases of chikungunya across the districts of Rio. And we estimated the association of minimum temperature with the relative risk. And it seemed to vary, but our model allowed us to estimate how much the effect of minimum 1 degree change or a change in temperature affected the relative risk, for how long this effect persisted, because we know that temperature tends to affect more the life cycle of the mosquito. Lais can talk better than me about this. So it's an indirect effect, and fixing the lag at which you include the covariate in the model might be challenging.
Okay, so what we did, it's introduced, we fixed a number of lag. In our case, it was 20 lag. And then we introduce 1 lag at the time. So the first lag, the second, until the 20 lag, and every time we run the model to see how it impacts the
Okay, and then
yeah.
shows the model.
Yeah.
I see. Okay, thank you.
But did you do the same thing? Because I'm curious.
No, we estimate,
okay.
we used transfer function models that allows you to estimate how long the one unit increase in the covariate affects the relative risk. And actually, Lais could come up with a map showing how these effects changed across the city. So
Okay.
yeah, it allowed us to better understand the relationship of temperature with the relative risk of chikungunya.
Okay,
But anyway,
okay.
I don't want to take more of the time. Thank you.
Thank you.
Any last questions for Dr. Nasri? Yep, I think you've answered everybody's work. So great talk. Nice to see it. And just so that everybody knows, next week's colloquia is going to be slightly later at 2:30 p.m. And we'll have Venkata Davuri give a talk then.